Hi there, we're going to be doing some quick research on some functions that are rational functions, what the graphs might look like. I'm just going to go into Google and do a quick search. Rational functions have 5 characteristics. They have x and y intercepts, they have vertical and horizontal asymptotes, and they also have holes. Let's take a look at some. And these are just random ones I found by doing a Google search. This is a pretty traditional 1 over x function. Here's one that's got 3 parts to it. There's a left, a middle, and a right branch. Look at the way that middle branch approaches both vertical asymptotes. And it has holes in it. You can't see them very well, but those little red dots are holes in the graph. Here's another one that's in 3 parts. Sometimes people say 3 branches. There's a left, a middle, and a right. The left and right look symmetrical in this case, perhaps. I don't see any x-intercepts. I do see 2 vertical asymptotes, 1 horizontal asymptote. Oh, and this one's got 1 vertical, 1 horizontal. Looks like it's got at least 1 hole in it. Here's one that's in 3 parts, 2 vertical asymptotes, 1 horizontal asymptote. That's probably along the x-axis, it looks like, on that one. Let's see. The center of that is a pretty traditional thing, but here's one where the center changes direction. It's not really a parabola, but it looks a little bit like it, doesn't it? But it's squeezed in between those 2 vertical asymptotes, that center thing. Again, a left, a middle, and a right portion or part or branch to this one function. Those vertical asymptotes split it into different pieces. Here's one, a little more traditional, 1 vertical, 1 horizontal. I do see a hole. That hole is nicely represented with a black circle right there. It's a pretty traditional way of graphing and showing where a hole in the graph might be. Here's one that's got 3 parts, a left, a middle, and a right part to it. No vertical or horizontal asymptotes drawn, but I can see that there are some. As a matter of fact, the horizontal asymptote looks like it goes right along the x-axis. Notice that the left and the right branches actually cross that horizontal asymptote, which is okay. But then when you get further away from the origin, when you get closer to infinity, it approaches the asymptote. And but it's a little unusual, but sometimes we do see them crossing once, sometimes even twice before it approaches infinity. So that's definitely a trickier one to graph and harder to figure out when you're looking at data on how to graph it. The next graph is really an interesting one here. This doesn't have a horizontal asymptote. It has what's called a slant or oblique asymptote. You can see the diagonal line there. It's got a vertical one right there, but then it's got this diagonal one that's not flat. It's not a horizontal. It's at a slant. You find that equation by doing long division. The degree of the numerator is 1 more than the degree of the denominator. You do polynomial long division, and the quotient that you get is actually the equation of the line that creates that slant asymptote. So that is a much more tricky graph to create. We probably won't see a lot of those. I want to show you something here in Desmos. I created a rational function. If I graph it, it looks here like this black graph. And we know that we've done enough simplifying at this point. I can predict that there's going to be a vertical asymptote and a horizontal asymptote, but let's factor this thing. Let's factor the top and the bottom and see what it looks like. Hey, it looks the same. Must be I did my factoring right. Notice both the numerator and denominator have an x minus 2. We're going to be able to cancel that out and get yet another equation for this function, x plus 1 over x plus 3. Let's graph that. And again, it appears to be exactly the same. It has the same vertical and horizontal asymptotes. The question to me is what happened to that x minus 2? And we're going to get to that in a minute. That x minus 2, the thing we canceled out, ended up being a hole in the graph. Let's look at the asymptotes. Let's look at the intercepts first. These are some key points here. I find the y-intercept, of course, by setting x equal to 0, and I get a 1/3. I find the x-intercept right there at -1 by figuring out what makes the numerator equal to 0, and clearly a -1 makes the top of that fraction equal to 0. Those are 2 of the main characteristics, 2 of the 5. The vertical asymptote is another one. You find that by figuring out what sets the denominator equal to 0. And if you put a -3 into that reduced equation that's highlighted in blue there, you get a 0 on the bottom, and you can't divide by 0. It's a vertical asymptote. Horizontal asymptote's trickier. The degree of the top is 1. The degree of the bottom is 1. If the numerator and denominator have the same degree, you take the ratio of the leading coefficients. So x over x turns into y equals 1 as our horizontal asymptote. And that's perhaps the trickiest thing to find. Notice, by the way, on this graph, the reduced graph, if I go to 2, oh, I had it, 2, the y value is 0.6. It exists. And that's because 2 is a valid thing in the domain of the simplified function. But you need to go back to the original one. You need to go back to this one. And notice here, now 2 is not a valid answer. When I get to 2, if I can do it, oh, I had it, hold on, right there, 2, undefined. That is a hole in the graph. Notice that it even changes in Desmos, went from a solid dot to a hollow dot. And so that is an invalid point. That's a Anyway, this I just wanted to show you this thing real quick. This is a little app I have that graphs functions, and it puts the holes in automatically. It's not like Desmos where you have to go looking for them. Anyway, I'm hoping that this helped you out. We talked about both asymptotes, we talked about both intercepts, and we talked about holes. I hope this helps you visualize where we're going with all this.